Hey, can you hear me? I suppose so. Good afternoon. First of all, I wanted to thank the organizers, I'm not sure if everyone is here, and the crew for making this conference happen and for inviting me. So maybe a round of applause since it's almost the last talk to the organizers and the crew. Thank you. So my name is Szymon Kaliski and this talk is called Walking in the Garden of Forking Paths. So first of all, who's familiar with the Garden of Forking Paths? 2 people. Oh, 3. Okay, so for those of you who are not, it's one of many amazing stories by Jorge Borges. This one deals with this infinitely expanding story in which every decision that is being made doesn't necessarily lead throughout a single path, but basically creates this garden of forking paths of all possible futures. And I'm going to talk to you today about some of the paths that I've taken recently and why I think they are interesting. But to start off, I'm going to show you some of the things that I've spent my time working on. Not so much to talk about them, but to give you context behind the ideas that I'm going to talk to you about later in the talk. So I studied computer science and interactive media, 2 different fields, and when I finished college, I did what everyone tells you not to do, which is I started freelancing right away and started from doing mostly generative art kind of stuff. It turns out if you do this for work, you mainly do advertisement, which I didn't really enjoy that much, so I moved over to doing more of database-based work, and then over time got more and more work, opened a small studio. There's 4 of us there currently. I think contrary to most companies in here, we're not hiring, but we can be hired, so you know. The studio is called Flow Control, and we design and build digital tools, data-driven interfaces in visualizations, and this is like where most of my days are spent. This looks like this mainly, so we deal with data-heavy web applications, complex interfaces. We also do things like visual, very high-level domain-specific languages. The one a little bit in the front is something we've made for a music startup when they wanted very high-level visual language for describing MIDI transformation. The one a little bit in the back is a domain-specific language for programming your smart home. I also do a little bit of art in my free time. Here's 2 audio-based installations. The one a little bit in the front is something we've made for Kids Art Biennale, where they were recording field recordings from the city and then they could play the map as an instrument. So it was a pretty interesting project working with kids. And the other one is another gallery setting interactive installation. I also do a little bit of teaching, both in university setting and mainly during workshops. And what I teach is not programming for the programming's sake, but programming as a tool for creative expression, mainly for artists and designers. So these are not people who want to work at the bank. These are people who want to just express themselves through technology, and code is another way of doing that. So this all brings me to the 3 main things I want to talk to you today, and keeping in mind that the context of where these ideas come from. So first of them is making programming a little bit more approachable. And who is familiar with this? Awesome. So this is the code editor, and the environment is called processing. It's one of the most famous environments for artists and designers, and was made especially for them. So it's Java based, but what you get when you start it is a very simple editor with just play and stop buttons. You write a bit of Java code, your window is created for you. You don't need to care about applets and all this crap. You just throw stuff on the screen and it works. And it's amazing when you do workshops or like try to get into coding and don't want to look at IDEs and stuff like Eclipse, and like I know a little bit about programming, and it still is confusing and hard. So I wanted to bring the same ideas to something like JavaScript. So now this is the language I mainly work in, and when I teach, switching my head to processing and then explaining that environment where I usually work in another one was a bit hard. So I made this little application where you just drag your JavaScript code on it. I analyze the AST, install all the dependencies that you use, and automatically run it, and also live reload when you make any changes. So you can basically start making code and throwing stuff on the screen as soon as you have a file. Anytime you save it, it live reloads. This is pretty good, and I use it often on workshops when I try to, skip over the first 2 hours of setting up everyone on the same environment. Here, Node and NPM and all the stuff is bundled within the application, so you just do a single download and you can run it. But it still forces you to write your code in a very linear, top to bottom, the normal way. So I'm really interested in, let's see if you can see that. Who can read the font? Anyone? Yeah. Bigger? Yes? So I'm really interested in notebook style of making code, so interleaving prose with code. And then at the same time, some of the most interesting notebooks, like, I'm not sure if you've heard of Observable, which is this JavaScript startup that does code notebooks. They actually turn them into direct acyclic graphs, so all of the cells are interlinked, and you can unwind the dependency and update them basically as you would do a spreadsheet. So one thing I don't like about notebooks is writing code in a text editor in a browser feels icky. So I made this little thing called Editable. And I'm going to show you a little demo, which is basically taking the, let's call it a sketch then, which is basically taking the ideas, let's save this file, let's hope that works, taking the ideas of notebooks, but allowing you to write them as you would write code normally. So it gives you one top-level new word called def, and this is all JavaScript. So we're going to an intro where we grab, we're going to write a bit of markdown. So hello maybe. And hello is there. A little bit slow, I'm not sure why. Basically, any change you make to that file, the code refreshes. That's all normal for now. Let's make a variable, let's call it R. We have one, then we can do the basic stuff that you would do. So for example, grab that variable and use it for some calculation. But then since all of those defines, basically the first word always is like the name of the variable, they are stored in this kind of database thing. You can do things like create another variable that uses two more that were created. Like if you read your code imperatively top to bottom, they were created after, but you can still use them this way, and all the code and the connections are unwind for you, and you can basically throw the ideas out. I use it mainly for sketching in code, and since this is running finally in a browser, we can do things like use DOM elements. Ooh. So we can make a little canvas window. We can grab the context from that canvas. And then maybe make a drawing function. And you can see I'm just drawing stuff wherever I want. And this is because of the graph unwinding. And this allows me also to keep the code on my local machine. So things with notebook or like anything browser-based is when they stop paying for AWS, you're left with nothing. And in here, these files I get to keep. Editable is on NPM. I can use it even offline. It doesn't matter. So, we get the normal rectangle on the screen, and I also can run like normal JavaScript tooling, like Prettier or whatever, to format the code. Basic idea being, I use Editable mainly for sketching, so for throwing ideas quickly together and being able to like try things out and don't worry about having a properly structured program. So obvious next step is what if you want to look at the code you're writing as a graph, since it's a graph in the background anyways. So there's a ton of visual programming languages, and here's one that I made some time ago, which was also testing the idea if that could work if you were only to use your keyboard to edit things. So you can create a new things. Let's create a number input, and then you can create like a logger. You can connect those guys together, and then now I need to use the mouse to use the UI, but basically it logs stuff out. Basic stuff, right? We get to move stuff around. Let's create a basic math, so maybe multiply these guys. Let's go in here, and let's make another number input, just to show you how this all composes. So we have, let's multiply by 2. So anytime I change something, it changes. Like this is the normal stuff that you're used to. The issue I have with tools like that, especially if they are huge and on a big screen, but also, you know, we can make it smaller. But even then, you still are forced by the tool to write your code at a certain level. And here, the level at which you write your code is pretty low. Like you need to, like I can't imagine using this, doing any complex math by arranging boxes like that. So what I did is I allow you to create the nodes ad hoc within the system. So we can create a new one. And there's a bunch of stuff in here that we don't care about. So let's create one that just multiplies by 2. It's going to have a single input and a single output. And there's a bunch of crap that we don't care about. And we don't need any of these guys. So there's a lot of things that you can do within here. And the API is not the greatest, but again, I see some people from academia, so I won't say research. It's just experiments. But basically here we have the basic code to multiply thing by 2 that we can put in the box. It receives an input, it subscribes to it, and anytime it changes, it outputs a new value. So now we have a box that basically still does multiply by 2, but we moved up a single level of abstraction. And this, since this is working in a browser, we can do things like, you know, create an SVG element. So for example, we can make a circle in here. Let's wire this up. And then maybe if we put another logger in here, we can see what the circle is. So, sorry. If I change the size, you can see the logger now shows some metadata. And this, if anyone does any front-end programming, this basically is a React element flowing through the system. So now we're not creating just numbers, but we're putting like whatever we want throughout those connections. So we can, you know, throw in a container for it, and then maybe init. Let's see it on the screen. So this is, again, just an experiment, but I can imagine my developer environment at some point being able to throw in single like ad hoc debugging stuff and little visualizations while I develop this thing. So a little bit similar to the idea that I'm not sure if you attended Tudor's talk, but of moldable development. Here I can see something that you can mold as you work with it, because you can create visual elements within the environment that you work with. So all of those demos are online on my website as well if you want to play with them. So this brings me to the last bit of work in this space, which is I made an editor very inspired by processing, but adding some new ideas to it. So basically the normal structure is, as I would suspect, there's a code editor, we have some running canvas, we have current state visualization, and then some errors. Hopefully we won't get any. So the first interesting thing is this bar on the top here. So all of the code that you write is this little like library /DSL in which you create two main functions. There's update and draw. So update receives current state and produces new state. And even though I mutate it within the update function, it's immutable outside of it. And then draw receives that state and returns a bit of DSL for drawing things on the canvas. So I can snapshot the state over time and do things like, you know, scrap through history and see how it looked like at a specified point in time. And you can see at the same time the state representation here changes. We of course get things like basic live editing things, since this is all in a browser and I eval the code. I can move the rectangle around. I can change the background color. All the stuff that you would expect. What else? This, of course, is an editor still, so you can write your code in here. So let's make a red. Yeah, let's give it a position. And let's give it a size. And yeah, so there it is. And you can see also when I hover over things in the code, the relevant part of the code highlights, and it even works with the new one that was just created over here. So to do this, there's a bunch of AST transforms happening, and it even works if you have a lot of things on the screen or created them ad hoc. And the last point that I'm going to talk about a little bit later is usually code editors and doing any sort of like visual or musical stuff with code generative art, you go from textual representation to the visuals you see on the screen. Anytime you want to change something, you need to switch your back brain to working with textual representation, change the code, compile, hopefully it works, you see the new thing. In here, I wanted to try if it's possible to make this manipulatable both ways, so I can drag this rectangle around, and you can see the code reflects, and it finds where the relevant position of that rectangle comes from and changes it. And it also works with the new one that I just created, and of course we can start the animation again, and it starts to animate. So we're going to get back to how it works towards the end of the talk, but I want you to like keep this in the back of your head and maybe try to figure out how you would implement something like this. So basically the same is declarative creative coding in DSL, so very small language on top of Canvas. It gives you time travel, live coding, and direct manipulation. All of this stuff, like in separate, I think is not super exciting, but together it creates a kind of interesting thing to explore further. So I think this is going to be like a repeating theme over this talk. If you like some of these ideas, take it and by God make them better, because I just play around. So this brings me to making programming a little bit more personal. So who knows what this is? This is a Lisp machine. Who has heard of Lisp machine? Awesome. So they had a lot of interesting capabilities, one of which was Lisp machine was written in itself, similarly to like Smalltalk and Faro work. So basically you could prod and interact with a living system while it was running. So besides me being at my studio, I'm also a researcher at this independent research lab called Ink and Switch. And one of our past projects was called Capstone, and now there's a new iteration of it called Muse, which was this tablet-based application, a studio for ideas, a thing you can think with and come up with new solutions to your problems. So in Capstone iteration, it was based on basically being able to throw stuff on the screen, which you see in the upper part on the screen running on tablet. And my research was around interacting with this. So I wrote a little REPL connection to the Capstone system in which you can basically access whatever you see on the screen and then mess with it. So we can change background, not something exposed by the system, but something you can do if you have the live connection to a living system. We can also change things on your workspace. The API is not great, but it was mainly testing the idea of like how it would work like if you have a REPL access to the system that you're using. And of course you can do crazier things. One of the ways we explored is to expose some hooks, so you can hook into the system, and in here we're hooking into dragging the cart and then doing a bit of math to basically create a grid-based system, something again not given by your system, not designed by a developer, but something you want. You can change a piece of code and run with it. And I'm really interested in making our systems like that. So for various strange reasons, I wrote my own window manager for Mac OS X, mainly because I hate moving windows by mouse. And this is, idea that is available in all the Linux distributions, not here. It took a lot of work and a lot of hacks, and it's based on, hidden macOS APIs that change version to version, and it breaks all of the time. And it shouldn't be like that. It should be possible to build those things and change the code that you run while it runs. And somehow all of these devices turned into appliances, like it's the same as a toaster. You can, toast the toast, but that's it. And computer shouldn't be like that. Obviously, we're making these slides. I want to see slides in context, and so I'm not bashing on something, it's a different idea than open source. I could imagine writing my slides in PowerPoint equivalent in OpenOffice, but then what I want is this. I want to be able to see my slides in context as a gallery, and this is something I can't do, even though I can download the PowerPoint version of OpenOffice. hacking it and being able to like change the code, compile it, that would take a lot of work. And at some point, it's simpler to just write your own. What I'm trying to say is it shouldn't be like that. It shouldn't force you to write your own slide software because you want overview of your slides. It's crazy. So here's some interesting links. I really need to plug in Ink and Switch because they allow me to do this kind of work. We have end-user programming article about this sort of stuff that I encourage you to check. There's also two systems that we explored, Pushpin and Farm, done by my colleagues, both of them based on CRDTs and being built as hackable open systems. Radical is another interesting idea, not from us, about using IPFS for sharing programs. So this brings me to the last part of this talk, and I think the most hand-wavy out there idea. So who has seen this? Who knows who this is? Okay, so there's no audio on the video, so I'm going to narrate over it. This system is called Sketchpad. It comes from, I have the time somewhere, 1963 by Ivan Sutherland. And he basically created his own display and his own pen. And he's right now just drawing a bit of architectural design, but then he can, by pushing those buttons describe relations between things. So at some point he's saying that all of these three lines should be perpendicular, I think is the English word, and then the system solves it, right? So this is amazing. And this is something 1963, and we still don't have this in our own like day-to-day stuff. This is another example of something similar. Who has seen this? Yes, ThinkLab. ThinkLab by Alan Burning, 1979. Again, no audio, so what you see here, it looks a little bit like a similar system I showed you that I've made, just the graphical language. There's a multiplication over here and addition over here. We have some constants. Constants have these anchors. They anchor, they don't change. So he describes what this is and now uses it as a blueprint of a bigger system, in which he added input and output over here. And what it does is you can see the numbers, but it's doing temperature conversion from Celsius to Fahrenheit. So at some point in the video, he changes the value of Celsius, and what you would expect happens. Like the value propagates, multiplies, the addition happens, and he gets a new value on the right. If you look, yeah, here he changes the value. Then we need to wait a little bit since computers are slow, and then we get the result. If you want, you can look for ThinkLab online. There's a whole video narrated by the creator himself, top-notch stuff. The value propagates and number here changes at some point. There it is. And now, since the system is actually not working as an imperative code or like procedural or whatever you want to call it, it's not calculating one way, it's basically trying to find stasis. So he can change the output value and propagates the error back and changes the input value. So the system works both ways, forward and backwards, which is super interesting and something, again, we don't have today. So again, Sketchpad, ThinkLab, both worth reading about. There's rich history behind those things, and this way of programming got somehow lost in the history, sadly. So how do they work? Who knows what this? I ask a lot of questions today. Anyone familiar with this kind of image? So this is gradient descent. So this is a meta algorithm, basically an algorithm that runs on your algorithm that tries to find a local minimum, a zero. And it can run alongside many input variables. So they are used mainly right now to train neural networks, something I'm not necessarily so interested in. But we can use this to basically, anytime you can return a distance from your solution, you can use it to magically get that solution. So if we go to JavaScript world and imagine we have this magical descent function, here is how we would use it. We need a starting point, here an x0, and then the descent algorithm runs with that starting point and gives us a test value that we need to say how far away it is from the local minimum, from 0. And here we're doing like obvious thing of trying to find a number equal to 100, we need to do a one-dimensional distance, 100 minus x. Since we can approach this from both sides, we do absolute of that, and we know how far off we are from 100. And then while the algorithm calculates, it will give us a value close to 100. And note that we never explicitly stated the problem, but we stated how far off we are from the solution, which is totally different way of thinking. So how can we do this temperature conversion that Ivan Soderland did 40 years ago? I have another coding example here. Let's see if it runs. Okay. So yeah, we're going to build a temperature converter. So we have two sliders. They don't work at all. This is basic, the most basic JavaScript code you could imagine. There's some inputs. There's a span with the value and a label. So we have a state where we hold temperature in Celsius and state where we hold temperature in Fahrenheit. So if we want to convert the conversion, we're going to set temperature in Celsius in here, and then see that the slider does actually move, but it never converts to Fahrenheit. So we need to do the math. We're going to set the temperature in Fahrenheit, which is going to be multiplied plus 32, hopefully. So now we have a value in Celsius converted to Fahrenheit, and of course Fahrenheit doesn't work. We need to do the same thing here. We're going to set the temperature in Fahrenheit and also in Celsius. So we need to, what do we need to do? I'm very bad at math, as you can see. Like so. So now, any way we scroll this, it works. The issue I have with a solution like that is basically we're writing the same code twice. Like, we know what the equation is, but we need to write it one way from Celsius to Fahrenheit and another way from Fahrenheit to Celsius. So this is something, and again, this doesn't require such a complex machinery that I'm going to show you, meaning like the gradient descent algorithm. You can do this much simpler, but I'm going to show you as a means of understanding how this stuff works behind the scenes. So we're going to ignore calculating one temperature from another. So I removed all of the handmade conversions. So now the slider works either one or the second one. And now we're going to try to find this stasis, this situation in which both numbers are equal. So we're going to use an effect, which is basically saying that we want to run this piece of code anytime a temperature in Celsius or in Fahrenheit changes. And now we need to describe our problem. So we're going to get a result from the uncmin, which is a gradient descent function, unconstrained minimization. I might be clumping a lot of things together, but the main idea is the same, trying to find a local minimum. So this is going to give us new input temperature, or like test temperature in Celsius and Fahrenheit. And we get our callback, and we need to provide it with starting points. So starting point for us is going to be vector of current temperature in Celsius and current temperature in Fahrenheit. Idea being that the input temperature in Celsius and Fahrenheit is proposed by the gradient descent. We tell it how far along we are, like how far away we are from the stasis, and then it calculates the results for us. So we need to do the conversion once. We need to basically describe both values in the same search space. So I'm going to just convert quickly temperature Celsius in Fahrenheit, and this is going to be once again 32. And then goes the fun part of returning like how far off we are. So we basically want a situation in which the test temperature in Fahrenheit is equal to temperature Celsius in Fahrenheit. This is something we can't write in this way, so we need to find the local minimum. So if we just remove one, subtract the values, and then again we need the absolute value because we can approach this from both sides. We now describe the equation that when solved will give us the same value for Celsius and Fahrenheit. And then we need to finally update our state. Result solution. So since temperature in Celsius is first item in this two-item vector, we're setting it as a solution 0, and then temperature in Fahrenheit is solution 1. And let's see. So you can see now I described the problem only once. I described basically how to convert Celsius to Fahrenheit, but any part of the slider I start dragging, it calculates the other one. You can also see the algorithm working because like the other slider is kind of slowing behind the first one while it's trying to calculate the result, the value, but you state your problem once and it works forwards and backwards. It doesn't care as long as there are inputs and things towards which to propagate the error. It can figure out the solution, which for me is this amazing black box, and I'm like, I have no idea why nobody is using this. So how does this work? The idea is the same. I can basically throw out the magic of some AST transforms. If we have a very basic drawing function which just draws a rectangle based on some state and some constants, I can pull them out into a vector and then use that vector and gradient descent to optimize that function, where the optimization target is how far off the position is from the mouse cursor. So I'm basically trying to find a solution for this program where the thing I'm dragging is where I want it to be, which is a very strange way of stating a problem, but as you could see, it works. So at Ink and Switch we used gradient descent and similar algorithms for few of our research tracks. Hopefully, there's more that I'm going to show you to you today, and again, these are extremely crude demos. Hopefully, there's going to be an article about that sometime soon, but for now, let's just see. So first one is, let's remove everything here. First one is this simple drawing application. You can imagine this rectangle as being something drawn by hand, and I can drag it around, but again you can see like it kind of hangs behind for a while. That's because I'm not dragging it, I'm optimizing the function in which the rectangle exists and trying to find such a position where it's closest to the mouse. So I can create, my own custom function. Maybe let's allow it to grow up and call this function. And in here, let's just snap to the top. So we have one additional rectangle. I can still drag the green one, but dragging this one doesn't work. That's because in this local function, there's nothing that will make it move. We can do this interesting thing of, calling itself recursively. So now we have infinity, and we can still drag this guy around, and they just infinitely snap to the top. We can add maybe a scale to the equation. So now when I drag it, or maybe not, when I drag it, you can see infinity is 12 in this situation. When I drag it, it tries to find a scale at which it's closest to the mouse again. So I can drag whichever one I want, and it does the proper thing because they all have IDs behind them, and I know which ID I'm dragging and which distance should be closest to the mouse. And this, of course, we can add a move operation to the mix as well and drag it around. And this, allows us to do things like Christmas trees. So as you can see, it's not super smooth, something to work on, but again, keep in mind this is all running in a browser in JavaScript. Running numerical methods in this environment is not great, but you can build this stuff and you can play around. And another thing, again, deleting all of that. Another experiment using gradient descent as a main algorithm driving what we did. This is actually a thing you can draw. And then you can see we have some properties on whatever I drew. So when I start dragging it over, again, optimizes. If I want to drag it from the bottom, this strange thing happens. So that's because, as you can notice in the sidebar, when I drag the bottom point, both the Y position and the height change. That's because they both influence where this point is, and the error propagates to both of them. That's why both of them change. If I want to keep it locked somewhere, I can do what you do in Excel. And now when I drag either top or bottom button, it basically sticks at this point. So we can explain, again, simple thing like how addition works, for example. So if I draw 3 of them, I can start specifying, like, I want all of them on the same position. So I'm going to input it in here. And now let's say that the height of the last one is going to be sum of the heights of all the other ones. So we have a little bit of math. And now anytime I change one of them, the other one changes, right? Basic stuff. But now I can change the result in here, and you can see again the error propagating back to the two that are already there. And again, since both of them influence that result, the error is propagated equally to both of them and then change. You can do a little bit more with this tool, but I'm not sure I have time to go deeply into that. So hopefully that article will come soon. If not, ask question after the talk. So, like I said, there's been a lot of research in those things, and I highly encourage you to play around and take photos. I hope to put a slide somewhere online so you can play with this. It's super interesting history, bit of computer history, and something again not that super explored. So I encourage you to play around. So this brings me back to what I was trying to say throughout this talk of making programming a bit more approachable, a bit more personal, and a little bit backwards if you can. I want to say that there are still things that are worth exploring and trying out, and again I hope some of you will find some of this interesting and make those ideas better and develop them further. I think that's it. Thank you.
We have time for some questions. Yep.
I was just wondering if you'd seen Quill in Clojure, so they have a functional mode where the state isn't transformed, you return a new state, yes. And it looked a little bit like one of your examples.
Yes, that was very much inspired by Quill.
Ah, great. And the other thing is the final example made me think of computational geometry stuff. So I was a maths teacher for a little while, and doing compass and ruler constructions, but then being able to change the width of the circle, say, or is really good for people's intuition, because you build up an intuition by interacting with something that you couldn't yourself do in 1,000 examples of or whatever.
Yes, exactly. Like the whole idea around constructive geometry is something super interesting, and the demo I showed of Sketchpad, I think, was dealing mainly with constructive geometry. Like he draws it by hand, but then the things are turned to be vector graphics, basically. We wanted to explore in this part of research something more hand-driven, mainly because we at Ink and Switch believe, drawing something, the modality of the idea, how well constructed the idea is, should be how well constructed your tools are. So sketching something on the paper is quick because your idea might not be there yet. If you want to use something like a vector graphics tool, you kind of know what you're doing at this point, right? So we wanted to explore how you can work and program systems live while sketching, basically. And this is where this idea came from, and that's why the lines are squiggly.
I can't remember if they're bidirectional, and I got a little distracted trying to look up while you were talking, because you were talking about so much awesome stuff so quickly. Jerry Sussman has a thing called propagators. I don't know if that's better than the back propagation thing you're trying in order to go bidirectionally on the functions.
Might be, I'm not sure, but yeah, basically the propagation usually is the back propagation of things. That's why we have back propagation when training neural networks. It's a big part of the thing. It's basically this. It's assigning values, the weights to the connections as it goes back to minimize the error. We're doing the same, but kind of live and in different context, but using the same techniques. I'm not sure if that's what you were asking, but
I'll send you a link.
Okay.
Any more questions? Yep. David?
Yeah. One, I guess, have any of these tools been used to make finished pieces, quote-unquote finished pieces, and how does this sort of tooling affect, sort of influence the output? Because of course tools always influence how we make things, and I don't know. Do you have any thoughts on that?
Yeah, so I didn't want this talk to last 2 hours, but that's a very important part. First we make the tools, then they make us, McLuhan, right? And I really strongly believe in that, whatever you use, makes the work you do. And I have a bit of stories around that, so we can chat afterwards. I don't want to take so much time. As for the production systems, most of what I showed you was experiments or demos. This one I'm using on workshops and for my own personal sketching, but it's just making doesn't require users to download the node to run JavaScript, and the one I showed you before here, again, in a bit more complex situation, I use that for sketching. In the work we do, usually the first part of the projects are usually not very well specified, so we do a lot of sketching, but sketching as producing something runnable, not sketching on paper, but producing a little demos for the client to decide which direction we want to take. The faster we can throw these ideas in and make them runnable and actually play with them, the better. So I try to make some of my tools work that way, and I use some of them, yes. I do a lot of dog fooding, as you can see, like this may be production ready. I use it, but I'm the only user. All of the rest is mainly, again, research or experiments or trying to find stuff out and find what works and what makes sense. Okay, thank you very much.
Oh, thank you very much. We have half an hour break until